Hello everyone, myself Dr. Santemi Kundu. I welcome you all to this lecture of soft computing techniques. This is the fourth lecture of module 6. So, in module 6, we are solving the numerical examples. Basically, we are solving some numerical questions with the help of genetic algorithm. In this class, we also solve two numerical questions. First one is that suppose there is a equality that is a plus 2b plus 3c plus 4d equal to 30. Genetic algorithm will be used to find the value of a, b, c, d that satisfy the above equations. First, we should formulate objective functions. For this problem, the objective is minimize for this problem the objective is minimizing the value of fx, where fx is equal to a plus 2b plus 3c plus 4d minus 30. Since there are four variables in the equation, namely A, B, C, D, we can compose the chromosome as follows. To speed up the computation, we can restrict the values of variable A, B, C, D are integer between 0 and 30. So here the one chromosome will be like that, A, B, C, D. So initialization, for example, we obtain the number of chromosomes in population as 6. Then we generate a random values of gene ABCD for 6 chromosomes. So that is chromosome 1 A, B, C, D. So we are writing A equal to 12, B is 5, C 23, D is 8. For chromosome 2 A, B, C, D, so that is 2, 21, 18, 3. For chromosome 3 A, B, C, D is 20, 4, 13 and 14. Chromosome 4 ABCD 21, 10, 6. Chromosome 5 ABCD 1, 4, 13, 19. Chromosome 6 ABCD 20, 5, 17, 1. So we need to find the fitness value. So fitness value of chromosome 1, that is A objective 1, is absolute value of these things. A plus 2b plus 3c plus 4d minus 30, so that is 12 plus 10 plus 69 plus 32 minus 30, so that is absolute value is 93. For chromosome 2, that is F objective 2, fitness, that is basically the fitness value of chromosome 2, fitness value of chromosome 2, that is you can write F2. So here we are writing F objective 2, so that is same thing, A plus 2b plus 3c plus 4d minus 30, so that is 80. Similarly, we are calculating the objective fitness value of 3, fitness value of 4, fitness value of 5, fitness value of 6. So we have calculated all fitness values. Next, we need to do the selection. So the fittest chromosome, we have higher probability to be selected for the next generations. To compute fitness probability, we must compute the fitness of each chromosome. To avoid divided by 0 problem, the value of F objective is added by 1. So here the fitness of 1 is 1 by 1 plus F objective. So that is F objective value was 93, so that will be the 94. So 1 by 94 is that is 1 by 94 is 0.0106. Fitness of 2, 1 by of 1 plus F objective 2, that is 1 by 81 is 0.0123. Fitness value of 3 is 1 by F 1 plus F objective 3, that is 1 by 84, 0.0119. Fitness 4 is 1 by 1 plus F objective 4, that is 1 by 47 is 0.0213. Fitness 5 is 1 by 95, that is 0.0105. Fitness 6 is 1 by 56, that is 0.0179. So if you add all this summation, you will get 0.0845. Next is that to the probability of each chromosome is formulated by pi equal to fitness I by total. So P1 is equal to fitness by total P2 is equal to fitness by total, which is 0.1456. P3 probability is 0.1408. P4 is 0.2521. P5 is 0.1243. P6 is 0.2118. From the probability, we can see that chromosome 4 that has the highest fitness, which is 0.2521. This chromosome has highest probability to be selected for the next generation chromosome. For selection process, we use roulette wheel that we would compute with the kinetic probability values, which are for C1 0.1254, for C2 0.1254 plus that, for C3 sum of all previous, C4 like that, and ultimately C6 is 1.0. So having calculated the cumulative probability, the selection process using roulette wheel, if the random number R1 is greater than C1, like that, this is C1, this is C2. If random number comes here, then C2 is second chromosome is selected. So if the random number R1 is greater than C1 and smaller than C2, then chromosome 2 is selected for the next population. So here we have used some random numbers, so we select chromosome 2 from that is as like new chromosome 1, chromosome 3, new chromosome 2, chromosome 1, that is new chromosome 3, similarly 6 chromosome is new chromosome 4, 3 is new chromosome 5, 6 is new the chromosome 4 is new 6 chromosome, so new chromosome 6. So chromosome in the population thus become chromosome 1 is that 0 to F2 B21 C18 D3. So chromosome 1 basically you can check the chromosome 2. So chromosome 2 is basically 221 18 13. So that become chromosome 1 in this population. So that is the chromosome 1. Similarly chromosome 2, chromosome 3, chromosome 4. For this example, we use one cut point, that is randomly select a position in the parent chromosome, then existing sub-chromosomes. So parent chromosome which will mate is randomly selected, and the number of mate chromosome is controlled using the crossover rate parameters. So chromosome K will be selected as a parent. The random number of kth chromosome is less than the crossover rate, then only it will be selected. Suppose I said that crossover rate is 25%, then the chromosome number K will be selected for crossover if random generated value for chromosome K, that is RK, is below 0.25. So we are assuming some random number, that is R1 0.191, R2 is 0.259, R3 is 0.760, R4 is 0.006, R5 is 0.159, R6 is 0.340. So our crossover rate we are assuming 0.25. So here chromosome 1 is selected, chromosome 4 is selected, chromosome 5 is selected, and this will not selected 2, 3, 6 as their value is higher than the 0.25. So for this 3 chromosome we will get another 3 chromosome by the crossover technique. So let's check it. So for random number R is above, the parents chromosome 1, 4 and 5 are selected for the crossover. So you do the crossover between 1 and 4, then 4 and 5, then 5 and 1. So after chromosome selection, the next process is determine the position of the crossover point. This is done by generated random number 1 to length of the chromosome minus 1. So here is length is 4, so that is 1 minus 1 to 3. So in this case, generated random number should be between 1 and 3. So we select the chromosome number. So after we get the crossover point, parent chromosome will be cut at crossover point and its scenes will be turn changes. So that is crossover technique, you know. For example, we generate 3 random numbers and we get 1, 1, 2. So for chromosome 1 and 4, after 1 we'll do it. So we'll get 1 chromosome which is 2, 5, 17, 1. So that is another chromosome, and chromosome 4 that is between 1 and 4. So here also the chromosome point is 1. So here we'll get 24, 13, 14. Then crossover point is 2, so here we will get 10, 4, 18, 3. So new chromosome, we have chromosome 1, then chromosome 2, then chromosome 3, like, so chromosome 3 is like previous one, only 1, 4, 5 will change, but and the rest 2, 4, 6 as it is. So just check it. That is 2 chromosomes, 10, 4, 13, 14. So here the chromosome number 2, 3, 6 will be the same, only we'll change it 1, 4, 5. So 2, 3 and 6 are the same. So here you can check that 2 and 3. So 2 is 10, 4, 13, 14. Just check 10, 4, 13, 14. 10, 4, 13. For 2 is same. Similarly 3 will be same and 6 will be same. Only chromosome will be changed here 1, 4, 5. This is the from previous. This will be the new chromosomes. This is new 1, 4, 5 and new, and this is from the previous. So we got the 6 chromosome. So now we need to do the mutation. So number of chromosomes that have mutation is determined by the mutation rate parameter. We can check mutation probability. Mutation process is done by replacing the gene at random position with a new value. The process is as follows. First, we must calculate the total length of the gene in the populations. So total length is, there is 6 chromosomes are there, each 4 length. So 4 into 6 is 24. So total is 24. Now mutation process is done by generating random integer from 1 to 24. If the generated random number is smaller than the mutation rate variable, then mark the position of gene in chromosome. Suppose we define mutation probability is 10%, that is 0.1. So here the total number will be changed 0.1 into 24, that is 2.4 approximates 2. So we can change only the 2 genes. So here we can change only the 2 genes. So here chromosome 1, 2, 5, 17, 1. Chromosome 2 is 10, 4, 13, 14. Chromosome 3 is 12, 5, 23, 2. Chromosome 4 is 24, 13, 14. Chromosome 5 is 10, 5, 18, 3. Chromosome 6 is 21, 10, 6. So we'll change only 2 genes. So that will be changed by random numbers. So we change this is, so that is basically 14. So we keep so that is chromosome 3, that is 8. So we change it like 2. And so after mutation, after this change, we change here. So after this change, we'll get this new chromosome. So we'll this will consider a new populations for the next generations. Now we have chromosome 1, which is 2, 5, 17, 1. So the value of the objective function is that 2 plus 2 into 5 plus 3 into 17 plus 4 into 1 minus 30. So that is 67 minus 30, 37. But the chromosome 2 is 10, 4, 13, 14. So the objective value is absolute of 10 plus 2 into 4 plus 3 into 13 plus 4 into 14 minus 30. So it is 113 minus 30, which is 83. Now the chromosome 3 is 12, 5, 23, 2. So which is 12 plus 2 into 5 plus 3 into 23 plus 4 into 2. So that is absolute value of 99 minus 30, which is 69. Then uh, 4 is 93, then 56, then 46. From the evolution of new chromosome, we can see that the function, objective function is decreasing. So that means we have a better chromosome or better population compared with the previous chromosome. So new chromosome for the next iteration we can solve the same thing, and in this way we'll get the best chromosome. So here the best chromosome will be 7531. So A7, A, B5, C3, D1. So we'll get this. So this is the way to solve the uh, numerical questions by using genetic algorithms. So let's try to understand some on more questions. So here the question is that we want to solve the minimize questions. Minimize y equal to minimize y equal to 0.2 x square plus 450 by x, where x is a decimal point, that is 0 to x 25.5, 1 point decimal. So here epsilon equal to 1 by 10. 1 point decimal. So you know that 2 to the power n minus 1 is greater than equal to b minus a by epsilon. So here 2 to the power n minus 1 is greater than 25.5 divided by 0.1. So here 2 to the power n greater than equal to 255. So n is greater than equal to, you can say n is greater than equal to the 8. So there will be 8-bit string. Okay. So you can take any value from, so here the for 8-bit, so a, that is 0, can represent as 8 zeros, and that 25.5 can be represented by 8 1. So you consider any chromosome, like uh, any chromosome, so within that interval, so that is 0 0 1 0 1 0 1 0. So next is that 0 1 1 0 0 1 1 0 1. Next is that 1 0 1 0 0 1 0 0, and this is 1 1 1 0 1 0 1 1. So if we convert it in binary string, so you will get it that x is equal to, you can get it, that is basically 0 2 plus 8 plus 32. So x is 32 plus 8 plus 2, that is 42. So here you can write the decoded value, x is equal to p a plus b minus a to the power n minus 1 into x. So x is equal to a is 0, b minus a is equal to 25.5, minus 1 is 255, and x here 42. So that is 44.2. So that is x equal to 4.2. Similarly, this will be the 101. So that is 10.1. This is 16.4. This is 24. This is 23.5. So calculate the value of y. So that is 110.67. Then it is 64.95. This value is 81.23, and for this value is 129.59. So the expected count, as we are solving the minimized problems, those are minimum value, we count it for 2 times, and those are the maximum value, it will not at all counted. So we counted chromosome 2 for 2 times, 1 for 1 time, and 3 for 1 time. 4 is not uh, selected. So in the next stage, we will do the crossover and mutation. So for this question, we are assuming there is no mutations. So for the crossover, we are assuming that P1 is equal to, for the crossover, we are assuming that P1 is equal to the value that is basically the 2. So we are assuming that for P1 first pair, second pair, we are assuming that this is assuming as 2 chromosomes, so which is 0 1 1 0 0 1 0 1, and another is we are assuming that chromosome 3, which is 1 0 1 0 0, then again 1 0 0. So assuming that after the fifth, so C1 will get it as 0 1 0 0 1 0 0, and C4 we are assuming this is as 1 0 0 0 1 0 1. So that is C1, that is C4. Similarly for the parent, for we are assuming P3 as the same chromosome, which is 0 1 1 0 0 1 0 1, that is chromosome 2. And we are assuming another is that P4, which is 0 0 1 0 1 0, and that is basically the here chromosome 1 as P4. So again we are doing after fifth. So here also will get 0 0, that is HP2. It will get it HP2 will get it 0 1 1 0 0. Then lastly we'll get it 0 1 0. So and here we'll get 0 0 1 0 1 1 0 1. So that is the chromosome here you can 3. So this next iteration you can write it chromosome 1, this is chromosome 2, this is 3, this is 4. Again find the equivalent value. So for this value you will get it as 64 plus 32 plus 8, so that is 64 plus 32 plus 4. So you will get it 100. So here the new value will be 10.5. Next is 9.8, then 4.5, 16.5. So here the fitness value is 65, 65.12. Then this value is 104.05. This is 81.72. So this is minimum value. So we counted it for 2 times, and this is counted for 1. This is maximum value not counted, so that is counted at 0. Here we can count it at 1. So again we'll do the same crossover and mutation. In the next iteration we'll do the same crossover and mutation. So you will do another iterations. So in these questions we have solved two questions. So the question for today's class is that uh, try to solve similar questions by genetic algorithm. So these are the references for today's class. Thank you.